Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about Introduction to Nanotechnology, various types of nanoparticles and nanotechnology time. In this lecture video, I will discuss about properties of nanomaterials. So let's get started. Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. In this lecture video, I will discuss about properties of nanomaterials, which includes optical properties, electrical properties, magnetic properties, structural properties, mechanical properties, and finally I will discuss about physical properties. First of all, let's see optical properties of nanomaterials. Color can arise from various mechanisms such as here shown, the origin of the color, which is from absorption or emission, reflection or transmission, scattering, for example blue sky, dispersion, for example prism, interference, for example oil films on water surface, compact disc or butterfly wing. It is one of the most useful features of nanoparticles. It has a wide range of applications in visual science. Nanoparticles are helpful too in the optical experiment, thus used in manufacturing of various optical detectors, laser beam, sensors, and imaging technology. Applications in the display cell, photocatalysis, and the photoelectrochemistry are also very important. Nanomaterials exhibit a variety of unusual and interesting optical properties that can differ significantly from the properties exhibited by the same bulk material. By carefully controlling the size, shape, and the surface functionality of nanoparticles, a wide range of optical effects can be generated with many useful applications. An optical response in a nanomaterial can be created through several different mechanisms depending on the nanomaterial size, composition, and arrangement, and each method may provide certain benefits depending on the target applications. In optical properties of nanomaterials, let's see scattering, absorption, and extinction. When light is incident on a nanoparticle, it can be scattered or absorbed. The sum of scattering and absorption is referred as to extinction. Nanoparticles are in the size regime where the fraction of light that is scattered or absorbed can vary greatly depending on the particle's diameter. At diameters less than 20 nanometer, nearly all of the extinction is due to absorption. At sizes above 100 nanometer, the extinction is mostly due to scattering. By designing a particle with a larger or smaller diameter, the optimal amount of scattering and absorption can be achieved. Another byproduct of scattering, absorption, and extinction relationship between size and absorption scattering is that aggregation can increase the effective size of a nanoparticle, resulting in an increase in scattering. This is why 20 nanometer diameter silica particles are cleared in solution, but resuspensions of dried 20 nanometer silica particles aggregated will be a milky white color as shown in these two pictures. In optical properties of nanomaterials, let's see plasmonic nanomaterials. Nanoscale structures made up of metals such as gold, silver, and aluminum can support surface plasmons modes where the free electrons in the material naturally resonate at a frequency that depends on the composition, size, and the shape of the particle. When the wavelength of incident light matches the oscillation frequency, the particle can strongly absorb or scatter the light, resulting in a strongly colored particle. By tuning the size and shape, the peak resonance wavelength can be shifted across the visible and into the infrared region of the spectrum, allowing for a wide range of color tunability. In addition to metal nanoparticles, there have been recent examples of metal oxide nanoparticles doped with other metal atoms that shows strong and tunable plasmons resonances. By changing the particle size, dopant and dopant concentration, plasmon resonances in the near infrared and short wavelength infrared can be fabricated as shown in this picture. Gold nanoparticles with different sizes shows different colors. In this picture, gold and silver nanoparticles with different colors and sizes are shown. Here is the comparison of gold and silver nanoparticles. The respective TEM images are also shown here. The comparison between gold nanoparticles and silver nanoparticles with size of 100 nanometer, 50 nanometer, and 80 and 40 nanometers are shown here in this diagram. Now let's see the optical properties of quantum dots. Nanoparticles made of semiconductor materials, often referred to as quantum dots or QD, which absorbs and emits light at certain wavelengths that depend strongly on particle size and shape due to quantum confinement effects. By changing the size and composition of the quantum dots, their emission wavelengths can be tuned from the ultraviolet through the visible to the near infrared regions of the spectrum. For example, by tuning the size of cadmium-selenium quantum dots from 2 nanometer to 4.2 nanometer in diameter, the emission wavelength can be shifted across the visible spectrum, with the smaller particles emitting in the blue and the larger particles emitting red light. As fluorescent materials, quantum dots offers a number of advantages over organic fluorescent dyes. In addition to the ability to easily tune optical properties by varying particle size, the quantum dots are less likely to photobleaching under high-intensity illumination, offers comparable or larger quantum yields than organic dyes, and can be excited much further away from their emission peak, giving them a large effective stroke shift and allowing more flexibility with imaging or choosing excitation sources to avoid autofluorescence in biological samples. Quantum dots are used in a variety of applications including photodetectors, solar cells, light-emitting diodes, televisions, and for medical imaging. At Nanocomposites, we use quantum dots as components of multifunctional particles, typically for diagnostics and imaging. An example is a metal-colored quantum dot composite particle that is used in lateral flow diagnostic devices. Now let's see the optical properties of photonic crystals. Photonic crystals are periodic dielectric structures that are designed to form the energy band structure for photons, which either allows or forbids the propagation of electromagnetic waves of certain frequency ranges, making them ideal for light harvesting applications. A photonic crystal is a periodic optical nanostructure that affects the motion of photons in much the same way that ionic lattices affects electrons in solids. Photonic crystals occurs in nature in the form of structural coloration and animal reflectors and in different forms. This type of structural color has many examples in nature, such as the iridescent blue appearance of morpho butterfly wing, which is due to nanoscale periodic structures that reflects only blue wavelength of light. Structural color gives rise to the multicolored iridescence of opal gemstones, which are made from highly ordered assemblies of silica particles. Highly monodispersed nanoparticles can be used for the assembly of colloidal crystals, where dried particles will organize into a periodic assembly that can diffract light. Structural colors assemblies can also be created dynamically in solution using magnetically responsive particles, such as the particles shown here, which align into ordered structures in the presence of magnetic field. One more example, the optical properties of zinc oxide are the large size zinc oxide particles blocks ultraviolet light and have ability to scatter visible light. Hence they appears white. Whereas nano-sized zinc oxide particles also blocks the ultraviolet light, but they are so small as compared to the wavelength of visible light that they do not scatter it. Hence it appears clear. Hence a SEM image of zinc oxide nanoparticles is shown here, which is used in sunscreen creams. Now let's see Gimai theory for change in optical properties. Gimai explained the phenomena using Maxwell's equation in 1908. When electromagnetic radiation incidents on spherical particles of uniform size, a part of the radiation is absorbed and a part is scattered as shown in this diagram. Thus, the intensity of transmitted light changes. If the incident light has wavelength lambda, intensity I naught, and the length of medium is x as shown in this diagram, then the intensity of transmitted radiation is given by the equation I is equal to I naught exponential of minus mu x, where mu is equal to capital N upon capital V into capital C ext, where N is the number of particles in medium, V is the volume of colloidal particles, and CEXT is extension cross-section of a particle. At nanoscale, as size of the nanoparticles change, there is change in the length of medium and thus the value of mu and x changes. This changes the intensity of transmitted light and it depends on the wavelength of incident light. This changes the color of nanoparticles at different nanoscale region. Mai's theory successfully explained absorption of light of visible wavelength for nanoparticles. But for particle size less than nearly 10 nanometer, there is need to consider dielectric constant which depends also on nanoparticle size. This is all about optical properties of nanomaterials. Now let's see the electrical properties of nanomaterials. We know that every particle has some electrostatic property. Thus, nanoparticles also show a wealth of condition differently. This electrical conductivity plays a significant role in nanoparticles such as nanorods, carbon nanotubes, etc. Inside the nanoparticles, its energy band structure and charge carrier density can also influence the bulk particles differently. For example, high density electron storage is possible using quantum dot devices that use laser and light emitting diodes. The spacing of electronic levels and the band gap increases with decreasing particle size. This is because the electron-hole pairs are now much closer together and the Coulombic interaction between them can no longer be neglected, giving an overall higher kinetic energy. The increase in band gap can be observed experimentally by the blue shift in the absorption spectrum or sometimes even visually by the color of the samples. A larger band gap means that more energy is required to excite an electron from the valence band to the conduction band, and hence light of a higher frequency and lower wavelength would be absorbed. The comparison of energy band gap of metals, semiconductors, nanoparticle semiconductors, and insulators is shown in this diagram. It shows that the band gap of nanoparticles vary roughly between 0.1 electron volt to 3.0 electron volt, which is again depend on size of the nanoparticles and the material. Let's see comparison of IV characteristics of bulk conductor and nanomaterials. Electrical properties are characterized by the mean free path of electron, that is path of the electron collision due to atoms or ions. The mean free path changes at nanoscale due to collision and tunneling within the conductor. IV characteristics of bulk conductor is shown in this graph. When voltage V is applied across the conductor, current I flowing through it is governed by Ohm's law and has a linear variation as shown here. Similarly, IV characteristics of nanoscale is shown in this graph. If dimensions of conductor are in nanoscale, which is around 1 to 100 nanometer, there appears a region around zero voltage for which there is no current. A single electron is transferred by tunneling when the voltage is plus minus E upon 2C. Therefore, when the voltage is less than this electron cannot be transferred. This gives a region of zero current at low bias voltage, and this is known as Coulomb blockade region. The electrons are transferred when the voltage is plus minus E upon 2C. The repeated tunneling of single electron produces Coulomb staircase as shown in this graph. Electrical resistivity. The material of nano-sized grains have larger number of grain boundaries than corresponding polycrystalline materials. Electrical resistivity of materials having nano-sized grain is larger than the polycrystalline materials due to scattering of electrons at grain boundaries. For example, let's see the electrical properties of graphene. Graphene is a single layer or monolayer of carbon atoms tightly bound in a hexagonal honeycomb lattice. It is an allotrope of carbon in the form of plane of sp2 bonded atoms with a molecular bond length of 0.142 nanometer. Layers of graphene stacked on top of each other from graphite with a interplanar spacing of 0.335 nanometer. The separate layers of graphene in graphite are held together by van der Waals forces, which can be overcome during exfoliation of graphene from graphite. These properties are what enable graphene to break so many records in terms of strength, electricity, and heat conduction. Graphene is the thinnest compound known to man at 1 atom thick, the lightest material known, with 1 square meter weighing around 0.77 milligrams. The strongest compound discovered, between 100 to 300 times stronger than steel, with a tensile strength of 130 gigapascal and Young's modulus of 1 terapascal. The best conductor of heat at room temperature, around 4000 watt per millikelvin. It is also the best conductor of electricity known. Studies have shown that electron mobility at values of more than 2 into 10 raised to 5 centimeter square per whole second. Other notable properties of graphene are its uniform absorption of light across the visible and near infrared parts of the spectrum. In graphene, carbon orbitals 2s, 2px, 2py form the hybrid orbital sp2 with 3 major lobes at 120 degree. The remaining orbital pz is sticking out of the graphene's plane. Now let's see the sigma and pi bonds in graphene. Sigma bonds results from an overlap of sp2 hybrid orbitals, whereas pi bonds emerge from tunneling between the extended pz orbitals. One of the most useful properties of graphene is that it is a zero overlap semi-metal with both holes and electrons as charge carriers, with very high electrical conductivity. Carbon atoms have a total of 6 electrons, 2 in inner shell and 4 in outer shell. The 4 outer shell electrons in an individual carbon atom are available for chemical bonding, but in graphene, each atom is connected to 3 other carbon atoms on the 2-dimensional plane, leaving 1 electron free available in the 3rd dimension of electronic conduction. These highly mobile electrons are called pi electrons and are located above and below the graphene sheet. These pi orbitals overlap and help to enhance the carbon-to-carbon bonds in graphene. Fundamentally, the electronic properties of graphene are stated by the bonding and anti-bonding, the valence and the conduction bands of these pi orbitals. The scanning probe microscopy image of graphene is shown here. Now let's see the electronic band structure of graphene. Valence and conduction bands meet at the 6 vertices of the hexagonal Brillouin zone and from linearly dispersing Dirac cones as shown in this figure. Graphene is a zero-gap semiconductor because its conduction and valence bands meet at the Dirac points. The Dirac points are 6 locations in momentum space on the edge of the Brillouin zone, divided into 2 non-equivalent sets of 3 points. The 2 sets are labeled K and K prime. The sets give graphene a valid degeneracy of 2. As I already discussed, graphite is a stack of carbon atom layers. In these layers, carbon atom forms hexagons in honeycomb-shaped lattice. In 2004, physicists succeeded in extracting single atom thick layers called graphene. The properties of graphene are very unusual. Each carbon atom possessed 3 electrons that bound with the nearest neighbor atom electrons, thus creating chemical bonds. From each atom, a 4th electron is delocalized on the whole graphene layer. Metals and insulators differ in the energy bands of their electrons. In a non-conducting material, the energy bands are either full or empty and are separated by an energy gap. In a metal, one of the bands is only partially filled. If the energy of electron is represented in function of their momentum, the bands become parabolas. Graphene represents an uncommon behavior. The energy bands from 2 circular cones connected one with the another at their extremities These are called direct cones. There is no gap, unlike the insulator, but no partially filled bands, unlike metals. Due to these cones, graphene electrons behave in a very peculiar way. They all have the same velocity and absolutely no inertia. It is as if they have no mass, similar to what the theory of relativity predicts for a particle traveling at the speed of light. Let's apply a voltage between graphene and metallic layer separated by a very thin insulator. The resulting electrical field will modify the quality of electrons carrying the electrical current. For a given direction of the field, the upper cone fills up. This means that electrons are added to the system. For the other direction, the lower cone is depleted. This means that electrons of another kind are added, that is, holes. A similar device is used in semiconducting transistors, present day in any electronic equipment. Whether graphene can replace semiconductor is one of the challenges of modern research. Now let's see one more example of electrical properties, that is carbon nanotubes. Carbon nanotubes, that is CNTs, are tubes made up of carbon with diameters typically measured in nanometers. Unlike graphene, which is a two-dimensional semi-metal, carbon nanotubes are either metallic or semiconducting along the tubular axis. Rotating single-walled zigzag carbon nanotube is shown in this animated figure, and this is a scanning tunneling microscopy image of a single-walled carbon nanotube. Carbon nanotubes often refers to a single-walled carbon nanotubes, that is SWCNTs, with diameters in the range of a nanometer. They were discovered independently in 1993 by Professor Sumio Iijima and Professor Ichihashi. Here me with Professor Sumio Iijima at A3 Symposium, Korea in 2010. Professor Sumio Iijima is a Japanese physicist and inventor, often cited as the inventor of carbon nanotubes. Although the carbon nanotubes had been observed prior to his invention, Iijima's 1991 paper generated unprecedented interest in the carbon nanostructures. The electrical properties of carbon nanotubes depend on how the hexagons are oriented along the axis of the tube. The following figure shows the three orientations that are possible. First is armchair, second is zigzag, and third one is chiral. There has been considerable practical interest in the conductivity of carbon nanotubes. Carbon nanotubes with particular combinations of small n and small m, the structural parameters indicating how much the nanotube is twisted. It can be highly conducting and hence can be said to be metallic. Their conductivity has been shown to be a function of their chirality, the degree of twist as well as their diameter. Carbon nanotubes with the hexagons oriented in the configuration labeled armchair, hexagons are lined up parallel to the axis of the nanotube, have electrical properties similar to metals. When you apply a voltage between two ends of an armchair nanotube, a current will flow. An armchair carbon nanotube is in fact a better conductor than the copper normally used in electrical wire or any other metal. Researchers are developing methods to spin carbon nanotubes together to make low resistance electrical wires that could transform the electrical power grid as well as reduce the power consumed and weight of wiring in such power and weight sensitive uses as spacecraft and airplanes. Another use that these armchair carbon nanotubes are being considered for is to connect devices in integrated circuits. As devices in integrated circuits become smaller, it may not be possible to pattern narrow enough metal lines, so researchers are considering using armchair carbon nanotubes to replace the metal lines. The next two possible orientations of hexagons in carbon nanotubes shares electrical properties similar to semiconductors. Those with the hexagons oriented in a circle around the nanotube have a configurations labeled zigzag. Those with a twist to the nanotubes so the hexagons do not form any line are called chiral. These two configurations of nanotubes will only conduct an electric current when extra energy in the form of light or an electric field is applied to free electrons from the carbon atoms. Semiconducting nanotubes could be useful in building ever smaller transistors used by the hundreds of millions in integrated circuits for all kinds of electronic devices. The conductivity and resistivity of ropes of single-walled carbon nanotubes has been measured by replacing electrodes at different parts of the carbon nanotubes. The resistivity of the single-walled nanotubes ropes was of the order of 10 raised to minus 4 ohm centimeter at 27 degrees Celsius. This means that single-walled nanotube ropes are the most conductive carbon fibers known. The current density that was possible to achieve was 10 raised to minus 7 ampere per centimeter square. However, in theory, the single-walled nanotube ropes should be able to sustain much higher stable current densities as high as 10 raised to minus 13 ampere per centimeter square. It has been reported that individual single-walled carbon nanotubes may contain defects. Fortunately, these defects allow the single-walled carbon nanotubes to act as transistors. Likewise, joining carbon nanotubes together may form transistor-like devices. A nanotube with a natural junction, where a straight metallic section is joined to a chiral semiconducting section, behaves as a rectifying diode. That is a half transistor in a single molecule. It has also recently been reported that single-walled carbon nanotubes can route electrical signals at speeds up to 10 gigahertz when used as interconnections on semiconducting devices. Now let's see the carbon nanotubes junctions and cross-linking. Transmission electron microscope image of carbon nanotube junction is shown in this picture. Junctions between two or more nanotubes shown in this picture have been widely discussed theoretically. Such junctions are quite frequently observed in samples prepared by arc discharge as well as by chemical vapor deposition. The electronic properties of such junctions were first considered theoretically by Professor Lambin, who pointed out that a connection between a metallic tube and the semiconducting one would represent a nanoscale heterojunction. Such a junction could therefore form a component of a nanotube-based electronic circuit. The image shows a junction between two multi-walled nanotubes. Now let's see other properties of carbon nanotubes. Carbon nanotubes have high electrical conductivity and have very high tensile strength. They are highly flexible, can be bent considerably without damage. They are very elastic, nearly 80% elongation to failure. They have high thermal conductivity. They have low thermal expansion coefficient. They are good at field emission of electrons. They are highly absorbent. Carbon nanotubes have high aspect ratio, that is, length is equal to nearly 1000 into the diameter. So these are the other properties of carbon nanotubes. Now let's see the magnetic properties of nanomaterials. Material shows magnetic properties due to orbital and spin motions of electrons. Electron has spin and orbital magnetic movement. The vector sum of all the movements of electrons gives the total movement of the atom. Iron, cobalt and manganese have a net magnetic moment. Crystals of these atoms become ferromagnetic, in which magnetic moment aligned in the same direction. In bulk ferromagnetic materials, the magnetic moment is less than the moment in the bulk material. Presence of domains in one direction, but moments of different domains are in different direction. When bulk ferromagnetic materials are subjected to alternating magnetic fields, they show hysteresis for which the BH curve is as shown in this figure A. In nano-sized ferromagnetic particles, essentially consisting of a single domain, there is no hysteresis and the BH curve as shown in figure B. This variation in the magnetization is due to change in cohesive forces between the atoms when material is in the nanoparticle form. In magnetic properties, let's see the dependence of magnetic moment on the dimensionality of the system. There is an increase in magnetic moment per atom as we decrease the dimensionality of the system. This is indicative of fundamental differences in magnetic behavior between nanostructures and bulk materials. This effect is important as surface spins are usually not ordered along the same directions as the spins in the interior of the material. Thus, we expect nanocrystals with more surface to have less magnetic moment mu b per atom than bulk materials purely based on the surface effect. As shown in this table, the magnetic moment mu b per atom for 0 dimension, 1 dimension, 2 dimension, and at the bulk level are shown for nickel and Fe, that is iron. For the 0 dimension, nickel has 2.0, whereas for Fe it's a 4.0. For 1 dimension, nickel 1.1 and Fe 3.3. For 2 dimension, nickel 0.68 and for Fe 2.96. And for the bulk nickel, it's 0.56, whereas for Fe it is 2.27. So there is an increasing in magnetic moment per atom as the dimension goes decreasing. Iron can have a maximum possible magnetic moment of 6 mu b per atom, that is 3 mu b orbital plus 3 mu b spin. This implies that in 0 dimensions, nanocrystals, very little of the orbital magnetic moment is quenched. Here are the TEM images of magnetic nanoparticles, where first is cobalt nanowires on silicon surface, and in second picture is a cobalt nanoparticle with the graphene shell are shown here. Here is one example of nickel aluminum nanoclusters, my research work which is published in Springer's Journal of Nanoparticles. The magnetic properties of nickel 13 aluminum N clusters with N is equal to 0 to 13 was studied, in which cluster magnetic moment decreases with the sequential substitution of nickel by aluminum atoms, which can be attributed to a greater degree of hybridization that forces the pairing of the electrons in the molecular orbitals of nickel and aluminum. Dark circles represent aluminum atoms and light circles represents nickel atoms as shown in these diagrams. For Ni7Al6, the complete quenching of the cluster magnetic moment appears to be due to the antiferromagnetic alignment of atomic spins. The graph shows the variation in magnetic moment of corresponding clusters. Initially, for nickel 13, the magnetic moment is 8.0, whereas for the Ni7Al6, the magnetic moment is 0, and finally for aluminum 13, the magnetic moment mu b is equal to 1. So this is all about the magnetic properties of nanoparticles. Now let's see structural properties of nanomaterials. Nanomaterials have different structural features in the arrangement of atoms and bulk materials. Most of the microstructure nanoparticles have some common characteristics. The properties go on changing by just a little difference in their size and arrangement. So dimensions of nanoparticles play a significant role in determining the properties. These fluctuations of properties amongst the nanoparticles are due to their sizes. The following characteristics are responsible for determining the properties of nanoparticles, which includes high surface energy, spatial arrangement, confinement in structures, and reduced imperfections. Dimensions of nanoparticles are tiny, so they bear a considerable surface area to volume ratio. Surface to volume ratio, which I have already discussed in my previous lecture. However, here is one example which shows high importance of surface to volume ratio in nanoparticles. It makes them more dependent on the surface, mainly when categorizing it considering the length of other nanoparticles. When the surface area exposed varies, then the entire surface properties get affected. Thus, these properties help in the enhancement and modification of bulk materials. For example, we can use metallic nanoparticles as an active catalyst for carrying out biochemical reactions. Chemical sensors from nanoparticles and nanowires enhance the sensitivity towards the sensor selectivity. The size of the nanometer has a spatial confinement effect on the materials. It is helpful to bring quantum effects. For the surface to volume ratio, a graphs of surface area A against volume V of the platonic solids and a sphere showing that the surface area decreases for rounder shapes and the surface area to volume ratio decreases with increasing volume. Their intercepts with the dashed lines shows that when the volume increases 8, that is 2 raised to 3 times, the surface area increases 4 2 raised to 2 times. The plot of the surface area to volume ratio SA to V for a 3-dimensional ball showing the ratio decline inversely as the radius of the ball increases. The structure of nanoparticles different from that of the bulk material. The crystal structure of large nanoparticles is same as the bulk material but with different lattice parameters. Electronic structure changes which leads to changes in optical properties and reactivity. Nanoparticles exhibit enhanced diffusion at elevated temperatures due to their high surface area to volume ratio. This property of nanoparticles allows sintering to take place at lower temperatures than in case of larger particles. While this diffusion property exhibited by nanoparticles may not affect the density of the product, it can lead to agglomeration. Research has also demonstrated that absorption of solar radiation in photovoltaic cells is much higher in nanoparticles than it is in thin films of continuous sheets of bulk material. This is because nanoparticles are smaller and can absorb greater amount of solar radiation. This is all about structural properties of nanomaterials. Now let's see the next property of nanomaterials, that is physical properties. Nanoparticles consist of three layers: the surface layer, the shell layer, and the core. The surface layer usually consists of a variety of molecules such as metal ion, surfactants, and polymers. Nanoparticles may contain a single material or maybe consist of a combination of several materials. Nanoparticles can exist as suspensions, colloidals, or dispersed aerosols depending on their chemical and electromagnetic properties. Physical properties of nanoparticles are dependent on following points, which are size, shape, specific surface area, and aspect ratio, agglomeration or aggregation state, surface morphology or topography, crystal structure such as FCC, BCC, etc., surface ligands or capping agents, the medium in which they are dispersed, solubility or melting point. So let's discuss all in detail with examples. The properties of nanoparticles are dependent on their size. Molecules, nanoparticles, and bulk materials can be distinguished by the number of atoms comprising each type of material. Note these are very approximate numbers. As the percentage of atoms at the surface increases, mechanical, optical, electrical, chemical, and magnetic properties changes. For example, copper nanoparticles are smaller than 50 nanometers, are super hard materials, and do not exhibit the properties of malleability or ductility of bulk copper. Surface to volume ratio is one of the important parameters which we have already discussed in previous slides. Next is aggregation and agglomeration. Aggregation and agglomeration are terms that are widely used by nanotechnology researchers to refer to nanoparticles that have associated into a clusters composed of two or more nanoparticles. Use of aggregate versus agglomerate is industry specific, but in the nanoparticle field, the two terms are equivalent and can be used interchangeably. The vast majority of dried nanoparticles are permanently agglomerated into clusters that consist of tens to hundreds or even thousands of individual nanoparticles, significantly increasing the effective size of nanoparticles and potentially altering the nanoparticles' physical and optical properties. The figure to the right shows a schematic of 2010 nanometer nanoparticles dispersed individually on top or clustered into 100 nanometer agglomerates on bottom. It is clear that the properties of these two nanoparticles are very different even though each contains the same number of identically sized nanoparticles. By applying shear forces to nanoparticle agglomerates can break the agglomerates into two or more pieces. However, even with the most powerful dispersion mechanisms such as probe sonication, milling, it is typically not possible to restore agglomerated particles back to a monodispersed suspension consisting only of individual nanoparticles. This is due to, in part, to the relative strength of the van der Waals forces that bind particles together and the shear forces that can be applied on the nanoscale. In order to separate two agglomerated nanoparticles, forces in different directions have to be applied to each nanoparticle. Next is surface morphology or topography. Here morphology of nickel nanoparticles and silver platelets are shown in these pictures. Morphology, that is the study of form compromising shape, size and structure, is important for materials research in general. For nanostructure materials, popularly known as nanomaterials, morphology has a special significance in this case of physical and chemical properties. Unlike bulk materials, properties of nanomaterials are strongly correlated to shape. This shape is attained during growth through a self-assembling processes stated by the interplay of size and molecular interactions. Next is crystal structure. Most solids are crystalline with their atoms arranged in a regular manner. This arrangement of atoms impacts the functionality of the material. Some solids have this order presented over a long range as in a crystal. Amorphous materials such as glass and wax lack long range order, but they can have a limited short range order, defined as the local environment that each atom experiences. The spatial arrangement of atoms in a crystal lattice is described by its unit cell. The unit cell is the smallest possible volume that displays the full symmetry of the crystal. Many materials have a preferred unit cell, as shown in this diagram. In three dimensions, unit cells are defined by three lattice constants and three angles. This leads to 14 Bravais lattices, each having characteristics restrictions on the lattice constants, angles, and centering of atoms in the unit cell. Most metals in the solid form closed pack lattices are shown in this figure. For example, silver, aluminium, copper, cobalt, etc. are face-centered cubic, that is FCC. Magnesium, zinc, etc. are hexagonal closed pack, that is HCP structure. Chromium, lithium, etc. can form body-centered cubic, that is BCC, as well as FCC and HCP depending upon formation energy. Next is melting point as a function of particle size. Nanoparticles have a lower melting point than their bulk counterparts. As the dimensions of a material decrease towards the atomic scale, the melting temperature scales with the material dimensions as shown in this diagram. Except a few low melting temperatures, which are less than 100 degrees Celsius, metals such as gallium and some metal alloys, most bulk metals have very high melting temperatures between 100 to over 1000 degrees Celsius at the atmospheric pressure. However, nanomaterials can melt at a temperature significantly lower than the bulk material. For example, the melting point of nanometer gold particles, 2.5 nanometer approximately, can be 300 lower than that of the bulk gold. The melting point of gold nanoparticles as a function of size is shown in these two graphs. Now let's see melting point versus shape. Particles may sinter together at lower than expected temperature. Rods can melt and form spherical droplets if heated too high. Thin films can form pinholes. Continued heating can lead to de-wetting behavior and island formations. In physical properties, the classification according to the number of reduced dimensions usually refers to the degrees of freedom, that is DOF, in the momentum. The density of states in bulk, that is 3D, 2D, 1D and 0-dimension semiconductor structure is shown in this diagram. For 0-dimension structures have very well-defined and quantized energy levels. The quantum confinement effect corresponding to the size of the nanostructure can be estimated via a simple effective mass approximation model. Systems in which carriers are confined in all directions, no free carriers. In 0-dimension, the quantization of particle motion in all directions, for example, quantum dots. In 1-dimension, nanomaterials have thin films or surface coatings and also used in the circuitry of computer chips and for anti-reflective properties and hard coatings on eyeglasses. These have been used in electronics, chemistry and engineering. In 1-dimension, the quantization of particle motion is in 2 directions. For example, nanowires. 2-dimension nanomaterials have fixed and long nanostructures with thick membranes. They are used to prepare nanopores, filters used for small particle separations and filtration. Asbestos fiber is an example of two-dimensional nanoparticles. In two-dimensional, the quantization of particle motion is in one direction. For example, nanosheets. In three-dimension, nanomaterials are fixed and small nanostructures where thin films are deposited under conditions that generate atomic scale porosity, colloids, and free nanoparticles with various morphologies. In three dimensions, there is no quantization of particle motion. For example, any bulk material. So this is about density of states as a function of dimensions of semiconducting materials or structures in 0 dimension, 1 dimension, 2 dimensions, and 3 dimensions. So this is all about physical properties of nanomaterials. Now let's see the mechanical properties of nanomaterials. Mechanical properties refer to the mechanical characteristics of materials under different environments and various external loads. Different materials exhibit different mechanical properties. As for the traditional materials, the mechanical properties of the metals generally consist of 10 parts, which are brittleness, strength, plasticity, hardness, toughness, fatigue strength, elasticity, ductility, rigidity, and yield stress. Most inorganic non-metallic materials are brittle materials which do not have properties such as plasticity, toughness, elasticity, ductility, and so on. Besides, some organic materials are flexible materials which do not have properties such as brittleness and rigidity. Nanomaterials have excellent mechanical properties due to the volume, surface, and quantum effects of nanoparticles. Hardness, elasticity, and ductility depend upon the bonds between atoms. Highly pure materials shows different mechanical properties than the bulk material. Young's modulus decreases in metallic nanocrystals with decrease in particle size. Yield stress increases with the decrease in grain size in bulk materials with nano-sized grains. Stronger materials can be produced by making materials with nano-sized grains. The carbon nanotubes are estimated to be about 20 times stronger than steel. Now here let's see the comparison of mechanical properties. As an example, let's see mechanical properties of carbon nanotubes and graphene. Carbon nanotubes are the strongest and stiffest materials yet discovered in terms of tensile strength and elastic modulus respectively. This strength results from the covalent sp2 bonds formed between the individual carbon atoms. Graphene 2 is the strongest material ever tested. In this table, material, Young's modulus in terapascal and tensile strength in gigapascals are shown. For the single-walled carbon nanotube, Young's modulus is 1 terapascal, whereas tensile strength is in between 13 to 53 gigapascal. For armchair carbon nanotubes, it's 0.94 and 126.2. For zigzag, 0.94 and 94.5. For chiral shape, 0.92 and 100. For multi-wall carbon nanotubes, the Young's modulus is 0.2 to 0.95 terapascals, whereas tensile strength in gigapascal is in between 11 to 63. For the graphene, the Young's modulus is 1 terapascal, whereas the tensile strength is 130 gigapascal. So this is all about the mechanical properties of the nanomaterials with few examples. This is all about properties of nanomaterials. In my next lecture video, I will discuss about nanomaterial synthesis processes. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.